Hey folks, we're finally getting into this kinetics thing. I'm awful excited. I love kinetics. It's what I do in my research, predominantly as an atmospheric chemist. You see a lot of atmospheric chemists that are into kinetics because it's all about thinking about how chemistry evolves in time. And as it turns out, that's a really interesting phenomenon for atmospheric environmental chemistry. How much time does this reaction take? Is it important to the time scales that we live on, and so forth? Okay. And so we're going to go through in this first section, this intro to kinetics, the basics, the fundamentals. All right. And then I hope we have enough time that I can really get into the interesting stuff, the techniques, the applications, and the advanced stuff. All right. So I'm just getting my make sure I had a timer going so I don't talk too long. All right. So let's get it going. So the first thing that I want to discuss is reaction rates. Okay. And so we're going to define the reaction rate. Let me get a thicker color there. There we go. So I'm going to say rate equals. Okay. And I'm going to first do this in terms of all of like the very correct physical chemistry terminologies, and then we'll put it into terms that we're more familiar with. Okay. So by definition, the rate of a reaction is 1 over the volume of the system times dz dt. And if you recall, this z thing that we calculated, right? That's called our extent of reaction, which by definition is going to be the number of moles of species J under final conditions, right? Minus the number of moles of species J initially, all divided by its stoichiometric coefficient. Okay, so it's basically how many moles have reacted, in addition to its correct stoichiometric ratio. Okay, so now I could write that as still write 1 over volume times 1 over the stoichiometric coefficient times the change in number of moles with respect to time. Okay, and of course we recognize that the number of moles of species J divided by its volume is just simply going to be its concentration in molarity. Okay, so the rate of any one individual reactant will always be 1 over its stoichiometric coefficient times the change in concentration with respect to time. Okay, and so this is for a homogeneous reaction in a constant volume container. All right. So let's see here. Okay. And so now in terms of units for rate, okay, so our units, there's going to be 2 main sets of units we see. One is more appropriate for solution phase, and the other is more appropriate for gas phase. All right. So units will be, we know that molarity, right, is mole per liter, and per unit time is per second. So that's going to be mole per liter per second. And so this is more appropriate for the solution phase, okay, or liquid phase reactants. All right. But the standard units for gas phase reactions, they're a little obscure. It's a little, what you wouldn't expect necessarily, but it's in molecules per cubic centimeter per second for gas phase. And there's several reasons for this, and I'm going to be getting into that as we go throughout this semester, or as we go throughout this section on kinetics. Okay, so molecule per cubic meter per second. All right. And so for this gas phase, okay, just to give you some familiarity with that unit, molecule per cubic centimeter, all right? So we know that we can calculate that by saying N over V equals P over RT. So I just kind of quickly rearranged the gas law, all right? And so we know that that would give me mole over liter. So if we do that for just normal room temperature, so let's say 1 atmosphere and 298 K, I got my handy calculator here, right? So I can say 1 divided by 0.08206, okay? And then divided by 298. So that gives me 0.0, I'll do 3 sig figs, 409 mole per liter, all right? And to get that into a molecule per cubic centimeter, we know that in 1 mole, there's an Avogadro's number, so 6.022 times 1023, all right? And we know in 1 liter, there's 1,000 cubic centimeters, okay? So now if I take this number times 6.022 E23, okay, and then divide by 1,000, there we go. That is one of my favorite numbers, okay? So that equals I ran out of room here. Let's see. So I'll write that over here, okay? So that equals 2.46 times 10 to the 19 molecules per cubic centimeter. So what does that number mean? That's the density, the molecular density of atmospheric pressure. So atmospheric pressure is 2.46 times 10 to the 19 molecules per cubic centimeter. You don't have to memorize that number unless you're like me and we use that number all the time. And so that's the number that I know, atmospheric pressure, 1019 molecule per cubic centimeter. But it's kind of a good off the top of your head when we're comparing like mole per liter per second to molecule per cubic centimeter per second. There's a lot of molecules per cubic centimeter, okay? So I just wanted to go through that just as a reminder, right, of how we do that, okay? So now what I've got here, this graph, as you can see, time versus concentration. So we can see a reactant decays. And so if we were doing this for the simple reaction, A goes to B, okay? I'll remind you that the stoichiometric coefficient of A equals -1, and the stoichiometric coefficient of B equals +1. So what that means in terms of the rate of these two things, we will see that A has a negative rate, okay? And so the slope at any one of these points, the negative slope, right, equals the rate because A is disappearing. And then B, in this very simple reaction that I did, right, just A goes to B, okay, we'll see that B, the product, has a positive rate, so it evolves in time. And the slope at any one point along this reaction is the rate. It is this rate in mole per liter per second in terms of the molar concentration, or gas phase molecule per cubic centimeter per second, okay?